Welcome, dear students. So we have been studying the mathematical basis of finite element method, and in today's lecture, part C, we'll formulate our familiar bar finite element, two-noded bar element, using the Galerkin's weighted residual method. So today's outlines will be: first, we will briefly discuss what is the disadvantage of classical Galerkin's or classical Rayleigh-Ridge method. In fact, we have already studied this in the last class. And then we will see the concept by applying which the finite element method bypasses these disadvantages. And then we will go for actual formulation of the two-noded bar element, which you are familiar with, using Galerkin's weighted residual method. And while doing so, we will introduce what is the shape function. The concept of shape function is a very important concept in formulation of finite elements, all types of finite elements, and therefore we will introduce this concept to you. And then we will see what is a strain-displacement matrix, the general definition, and how we can formulate the element stiffness matrix from these shape functions and strain-displacement matrices. And we'll also see how to formulate the nodal load vectors. Okay, so let's start. So you all know that the principal disadvantage of classical Galerkin's or Rayleigh-Ridge method is that to find an admissible solution, that is the assumed solution which satisfies the essential boundary conditions, is the most difficult task in a problem. And usually, as the problem geometry becomes complicated, these tasks become almost impossible. Okay, so for 2D and 3D problems, finding a good quality admissible solution is almost impossible. Okay, I think you remember that in the last class we have seen that if I have a 2D plate, it's really difficult to fulfill the boundary condition along this x equal to 0 line within this limit of y by having a polynomial solution, polynomial assumed solution. Okay, we have discussed these details. So that is what is meant by this, that finding a good quality admissible solution is nearly impossible for 2D and 3D problems. Now, to overcome these, we resort to the finite element method, and now we must understand how the finite element method overcomes this limitation. Well, this is a typing mistake. It should be limitation. Okay, let me correct it. Limitation. Now, for overcoming this limitation, in FEM we introduce two fundamental concepts. That the solution domain, that is the geometry over which I want the solution, we discretize and divide the solution domain into various subdomains, and those subdomains are called elements. Okay, you remember, I think, that when you studied, say, the truss, analysis of truss using FEM, suppose I have a truss, a simple truss, you remember that we had divided them into different truss or bar elements. Okay, at the joining points we took the nodes, and these were called the elements. These are basically nothing but a bar element whose element stiffness matrix you were already familiar with. So the whole geometry is divided into these subdomains. Similarly, if I have a, say, 2D problem, say I have a rectangular plate, the one we just now saw. So what we can do is we can divide them into various smaller regions. Okay, maybe we divide them into some rectangular elements. Okay, or I may go for triangular elements also. Okay, so these are now 2D elements. So the subdomain, the domain is divided into these smaller elements, which are actually the part of the actual domain. Okay, and the advantage of division of the whole body into the elements is that we have simpler geometries compared to the whole domain. All right, and the assumed solution can be easily written, more easily written for the element than for the whole domain or the whole structure. Okay, and since the elements are small, therefore a smaller order solution, suppose a linear solution I can assume. Okay, if it is a bar problem, say I can simply assume that it's a over the element the solution say varies as a linear function of x, say a0 plus a1x. In the earlier class we have seen that if I have a bar fixed at one end, you remember we had solved the problem of bar fixed at one end and loaded at the other end, by classical Galakin's method, and we saw that if I take a linear solution, the natural boundary conditions were not satisfied. This natural boundary condition was not satisfied with a linear solution. We needed at least a cubic solution for that. And we also know that the exact solution is a cubic solution. But if we divide it into different bar elements in the finite element method, we will see that even a linear solution works very nicely, because since the element is a simple one, only two noded element, therefore even a linear solution gives good results. And while finding the assumed solution, we deliberately keep them simple enough in most of the cases, and using those simple solutions, while using those simple solutions, we need to just ensure that the assumed solution is integrable and differentiable to the required order. Okay, and the integral of the weak form will be carried out separately for each domain, and then we'll be adding it together. Okay, so that's how finite element method works. Now then, the other very important fundamental concept used in finite element is that you know that in the classical Galerkin methods, the assumed solution had some unknown coefficients. Say for example, we used say u tilde. Suppose I use a second order solution, say a0 plus a1x plus a2x square, and our job were to find out the values of a1, a0 and a2 from the given conditions. Okay, and by writing the weak form, we use the weight functions to find out these values. Okay. Now, in finite element method, what we do is these coefficients basically represents the solution and its derivative at these nodes. If I take a finite element, say I have a bar element, two noded bar element, say, then of the assumed solution, from the assumed solution, these unknown terms are actually the solution itself, or if necessary in some other problem, if I need derivative of the solution, then these unknown parameters are actually those solutions and their derivatives at these nodes. That's how they are formulated. Okay, and the solution of the problem at these nodes are called nodal derivatives. You are already familiar with the nodal derivatives. For example, suppose in this truss, you remember that we took two nodal degrees of freedom in each node, 1 and 2. Okay, and say in global degrees of freedom, I took this as 2 and this as 1 and 2, 3 and 4, and so on, right? So these are my global degrees of freedom, and for a single bar element, I have 2 degrees of freedom if it is one dimensional. In a case of a truss, since it is a 2D body, I have 2 degrees of freedom. So these are called nodal degrees of freedom, and these nodal degrees of freedom are actually the solutions of our unknown at these nodes. Okay, and this choice of these nodal derivatives is dictated by the required order of the derivatives to specify the essential boundary conditions. Okay, now how many degrees of freedom we will select, that will be dictated by the required order of derivatives to specify the essential boundary condition. And the quantities needed to specify the essential boundary conditions are the nodal degrees of freedom. Whatever are necessary to specify the essential boundary conditions, they are basically the nodal degrees of freedom itself. And in a finite element method, what we do, we express the solution over the element, the solution over the element we express in terms of the nodal degrees of freedom itself. We'll see a little later. And that is how we bypass the problem of satisfying the essential boundary conditions. What we simply have to do is that at the boundaries we need to have certain nodes. That's all. If I have sufficient number of nodes on the boundaries, then we will get a very good solution where essential boundary conditions are prescribed. Okay. Now, depending on the type of problem, I have different variables I need to specify as essential boundary condition. For example, suppose I have a second order problem, say bar element problem, bar deformation problem. You remember the differential equation of equilibrium. We had ddx of AE du dx, actually the approximate solution. So in the classical form we wrote u tilde d2u du tilde dx, okay, plus q times x if q is the traction force, that was 0. So this is comprising of second order derivative. Okay, that's why it is a second order problem. Similarly, a beam bending problem, you remember that the differential equation is of fourth order, so those are called fourth order problems. Similarly, we may have sixth order problem, etc. And in order to satisfy the essential boundary conditions, in a second order problem, I need to specify only the displacement u. In a fourth order problem, I need to specify the displacement as well as its derivative, that means the slope of the displacement. Say for example, I think you remember that if I have a cantilever beam, suppose I have a cantilever beam, you know that at the support the displacement is 0 as well as the slope of the deflection curve is also 0, right? The slope of the deflection curve is also 0. So I have to specify both u and u prime, u dashed. So in a fourth order problem, I need to have a solution which is differentiable up to its first order. Similarly, in a sixth order problem, I will have to assume a solution which is differentiable up to the second order. Okay? So, for a second order problem now, you see, for a bar element, say, since the essential boundary condition does not involve any derivative, only u is involved, therefore the nodal unknowns are itself the solution. So nodal unknown at the essential boundary condition, wherever essential boundary condition is provided, there the essential boundary condition will be fulfilled by the nodal unknown itself. Therefore satisfying the EBC is almost trivial. We only need to set that at that node the deformation is 0. That's all. Okay? Or if I have a truss, say, where one support, say, undergoes some settlement in this direction, then I need to say that this degree of freedom is equal to the amount of settlement. So like this, in a second order problem, fulfilling essential boundary condition is very trivial, easily done. Okay? So now let us go for, let us see what was the next point. Next, we formulate a two-noded bar element using Galakin's weighted residual method. So for that, let us take up a bar element. Okay. So now let us see how we can use a linear solution for a second order problem in the finite element form. For that purpose, let us use a two-noded bar element. Say I have a bar element. These are my end nodes, node number 1 and node number 2. And node 1 is at location x1 and node 2 is at location x2. And the length of the element is L, which I can get as L equal to x2 minus x1. Now u1 is the degree of freedom or nodal DOF at node 1 and u2 is the nodal DOF at node 2. Okay, so u1 and u2 are the nodal DOFs. Now let us assume that the u over the element at any point of the element is a function of location, of course, x, and therefore I take u as a0 plus a1x. Now we do not use tilde sign here, okay, because I know that FEM is an approximate type of solution, so we all understand that whatever we are getting is approximate solution. Therefore we don't need to specify that it's an approximate solution by writing a tilde over it. Okay, so we'll just write u over the element instead of u tilde, and we know that it is an approximate solution because it is FEM solution. Alright, so therefore my u is a function of x, which is a0 plus a1x, and now we know that at node 1 my u has a value of x1, u1, and at node 1 the value of x is x1. Therefore, if I put these values here, then what I get, u1 is a0 plus a1 into x1. Similarly, I know that u2 is a0 plus a1 into x2, right? And therefore I can find out the value of a1 by simply subtracting one from the other. If I subtract the first equation from the second equation, then what I get a1 will be u2 minus u1 by x2 minus x1, right? u2 minus u1 by x2 minus x1. Okay, and then I can use this value of a1 in any of these equations, and thereby I can get a0, right? So if I use this value of a1, in the first equation, then what I will get, therefore u1 is equal to a0 plus a1 is u2 minus u1 by x2 minus x1 into x, right? And if I simplify this, then what I'll get, so a0 will be my u1 minus this value, so u1 minus u2 minus u2 into x. Okay, let me keep it as it is right now. u1 minus u2 minus u1 by x2 minus x1 into x, and then now let me simplify it. So this is equal to x2 minus x1 u1 into x2 minus x1 minus u2 minus u1 into x. Okay, and this, after simplification, I can get, this is u1 x1, and here will I have minus u1 x1 and plus u1 x1 here, so that will cancel, and therefore I will get u1 into x2 here minus u2 into x. So therefore I will get finally, okay, let me expand it for your benefit, u1 into x2 minus u1 into x1 minus u2 into x plus u1 into x. Okay. Here I have done one mistake. This should be x1, right? This should be x1. So x1, x1. So this is x1, x1. And here it is x2 minus x1. And so this and this term goes. And therefore I have simply u1 x2 minus u2 x1, right? u1 x2 minus u2 x1 by x2 minus x1. Now if I use these values of a0 and a1 in the original equation of u, what I get u equal to this is my a0, u1 into x2 minus u2 into x1 by x2 minus x1 plus a1 into x. a1 was u2 minus u1 by x2 minus x1 into x. And then if I expand it, what I get u1 x2 minus u2 x1 plus u2x minus u1x divided by x2 minus x1. Now what I do is I take the terms containing u1 common. So in that case here I have x2 minus x. So x2 minus x by x2 minus x1 into u1 plus for u2 terms I have x minus x2 x1. So x minus x1 by x2 minus x1 into u2, right? Now these values let us denote it by n1 and n2, okay, where so writing this as n1 and this as n2, I can write u equal to n1 u1 plus n2 u2, or I can write in matrix form n1 n2 into this vector u1 u2. In other words, I can write this matrix as a transpose of its column matrix. So n transpose into this nodal displacement vector, because u1 and u2 are the displacements at nodes, so we can call it nodal displacement vector, and we are denoting it by d because u was used to denote the displacement within the element. Is not right? You can see that we have written u within the element as a0 plus a1x. So in order to avoid confusion, this nodal displacement vector I am writing as d. Okay, so my n matrix is a column matrix here, n1 n2, where n1 is what? n1 is x2 minus x divided by x2 minus x1. So x2 minus x by L, because x2 minus x1 is L. This is my n1, and since it depends on x, so I am calling it n1 as a function of x. I can explicitly write. Similarly, n2 is x minus n1 x1 by L, x minus x1 by L. So this is also a function of x. Now you can see one important property of this n1, these quantities n1 and 2 is called shape function. They are called shape functions. This is a very important concept in finite element, so that I can express the displacement anywhere within the element in terms of this product n times d, n times the d, where n is my column vector, of course, okay, n transpose into D gives me the value of U. Alright, value of U at any point X is n transpose into D, and these D are my nodal degrees of freedom. That means what we are doing? We are expressing displacement within any point on the element over the element in terms of the nodal displacements. Okay. Now you can see one thing. Let us see what is the value of n1 at node 1. So value of n1, value of n1 at node 1 will be what? X2 minus what is X at node 1? It is X1. So X2 minus X1 by L. So X2 minus X1 is already L. So L by L gives me 1. So it is L by L is equal to 1. And the value of N1 at node 2, what it will be? Value of N1 at node 2 is this X will be X2, so it will be 0. X2 minus X2 by L, which will be 0. Okay, so if I draw the variation of shape function N1 over the element, what I will get? Suppose this is my element, there is my node 1, node 1, there is my node 2, and if I plot the value of N1, if I plot the value of N1, then I will get a value of 1 here and a value of 0 here, and since it varies linearly over X, therefore this will be my plot of N1, right? So this is my value of 1 and here it is 0, and this is my N1X. Okay. So similarly, if you look into the value of N2, what is the value of N2 at node 1? Node 1 X is X1, so N2 will be 0 at node 1, and at node 2 X is X2, so N2 will be 1. So just opposite will take place, and therefore if I plot the value of N2 over the element, then I will get a value of 1 at node 2 and a value of 0 at node 1. Okay, so this is my value 1 and this is 0, and this is my N2, variation of N2 over X over the element. Okay, so this is another fundamental property of all the shape functions we will be using for finite elements, that the shape function belonging to a node N1 belongs to node 1, because why? Because my displacement, in writing the displacement I am writing N1 into U1. U1 is the nodal displacement at node 1, so that's why this N1 belongs to node 1. So any shape function which is defined for a node, that must have a value of unity at that node and 0 at all other nodes. Okay, in this case I have only 2 nodes, so at this node it has a value of 0, but in other elements you will have definitely more than 1 nodes. Say it is a 2D element, say a triangular element, I will have 3 nodes. So there the value of n1 for node 1 will have at node 1 a value of 1, and at all other nodes it must have a value of 0. Similarly, n2, which is defined for node 2, must have a value of 1 at node 2, and at all other nodes it must be 0. This is one of the fundamental properties of our shape functions. And another property of shape function is that so we can write some property of shape function. Property of shape functions. Whatever may be the kind of shape function, it must fulfill this property. Property of shape functions. Number 1, it must have a value of unity for which unity at the node, for which it is defined. Okay, this is one property, very important property of shape function, and 0 at all other nodes. Okay, then second property is sum of all shape functions at a point within the element must be 1. Unity. So therefore, if I have n numbers of shape function in an element, then sum of all ni from I equal to 1 to n must be 1, and it is true for any point within the element, including at the nodes. Okay, now let us see if it is 1 for any general point x in our element. Just add these two values, n1x and n2x. Okay, for example, let us add n1x and n2x. n1x is x2 minus x by x2 minus x1 plus n2x is what? n2x is x minus x1 by L, or x2 minus x1. So x minus x1, x minus x1 by x2 minus x1. So now let us simplify. Simplifying, I will get x2 minus x1, x2 minus x plus x minus x1. So it will be x2 minus x1 by x2 minus x1, and this is 1. So I have two shape functions. So when I have added both of them for any point x, I have got 1. Okay. So while defining shape functions, these two properties are checked always, so that those are valid shape functions. Otherwise, those shape functions will not give you correct results. Okay. So this is what is meant by a shape function. Okay. And the advantage is that I can express the deformation at any point within the element in terms of the shape functions and the nodal displacement vector. Alright. Now these shape functions are also called interpolation function. Okay. So there are other names for shape function. So shape functions are also called influence function, and they are also called interpolation function. This is more commonly used, shape function or interpolation function. Interpolation function. Why do we call them interpolation function? Because we are interpolating the displacement at any point within the element from the nodal values. Okay? You see this equation, it is an interpolation equation. At any point u, I am interpolating the values by using the nodal displacements. That's why we call it interpolation function. Okay? So interpolation because the displacement is interpolated the displacement at any point is interpolated out of nodal displacements or nodal derivs by these functions. That's why we call it interpolation function. Then we also call it influence function. Influence function because it indicates at any point, say if I consider a point here, say x, at x, it indicates the influence of node 1 on its displacement, which is this much. Okay, if I consider the displacement at this point, the value of n1 at this point is this, so and this n1 is related to nodal duf1, therefore this n1 indicates that at this point the displacement is influenced by this much by the nodal duf1, and influence of nodal duf2 at this point is only this much. Okay, so this gives me how much weightage of the nodal duf has on the displacement at a particular point with the help of this equation. whatever is the value of n1 at that point, that much influence the u1 has on u. Similarly, whatever is the value of n2 at that point where I am finding the u, this n2 has that much of influence. This n2 shows that u2 has that much of influence on u. So that's why we call it also, or call them also as influence function. Okay, so we call them influence function because they indicate the magnitude of influence of nodal displacements on the displacement within any point, displacement of any point within the element, displacement of any point within the element. Okay, that's why we call it influence function. So these are the properties and various names given to shape function. And why do we call it shape function? Because it shows whether the displacement is varying linearly or quadratically or cubically over the element by the shape of these functions. Since our n1 is a linear function, so displacement is varying linearly over the element between the nodal degrees of freedom. Okay. So now let us see the Galakin's weight functions, how it differs, how it changes in finite element formulation. So Galerkin's weight function in finite element form. Now in Galerkin's weighted residual method, you all know that the weight functions are the partial derivatives of the unknown coefficients, right? You remember that in classical Galerkin's method, we wrote that this Wi weight function, ith weight function, Wi was my partial derivative of the assumed solution with respect to the unknown coefficients, right? Now you have seen that in finite element form we have got that u is nothing but, say, n1 u1, where n1 is the shape function for node 1 and n2 u2, right? And here you all know that in finite element formulation my basic unknowns are u1 and u2. The nodal degrees of freedoms are my unknowns, right? And therefore, since these are my unknown coefficients, therefore what will be my weight function in this case? So weight function will be, say, for w1 it will be du du1, right? Because these are my basic unknowns, nodal degrees of freedom. So these are my unknown coefficient in this equation. So this is nothing but my n1, is not it? Similarly, actually it will be del, I should write del to be mathematically correct, but here del and d are same because it's a function of one variable only. So del u1 is my n1 from this, and similarly my weight function, second weight function is del u2, which is my n2, right? So these are my weight functions. Now by knowing these weight functions, now it is possible for us to write down the weak form for this element. All right, so let us do that. So before going to those weak form, let us note this, whatever we have learned, that in Fe form, in Fe formulation, shape functions performs the role of weight function. Okay, now let us go for the weak formulation, and for that let us again take that same bar element. Let me go to the next page. Now finite element formulation, so finite element for axial deformation, so let us take again this same two noded bar element. This is my bar element having nodes 1 and 2, and the nodal degrees of freedom are u1 and u2, and it is subjected to certain surface traction, which is q. Okay, so this is my q, and then the node 1 is at x1 and node 2 is at x2, and the natural boundary conditions are, at node 1 I have a load, compressive load P1, and at node 2 I have a tensile load P2. Okay, and now we all remember that our governing differential equation is this: ddx of ae du dx plus q is equal to 0 within this x, within this limit of x, when x lies between x1 and x2. This is my equation, governing equation. And the natural boundary conditions, as we have learned in classical method itself, we can express as ae times du dx at x equal to x1 is my P1, but it is negative because it is a compressive load. Okay, and ae du dx at x equal to x2 is P2. This P2 is positive because it is a tensile load now. Okay, now let us take the linear assumed solution. Okay, so let our u be equal to n1 u1 plus n2 u2 this we have already got, where what is my value of n1? n1 is x2 minus x by L, x2 minus x by x2 minus x1, which is length, so this is L. Let me write it down here that this length is L. Okay, I forgot to write it here. This is my L. Okay, and my n2 is x minus x1 by L, right? X minus x1 by L. These values of shape functions we have already got. Okay, now what we do, we write down the differential, because I need this du dx, so let us differentiate u with respect to x, and therefore I have u dash x is what? U dash x is n1 dash into u1 plus n2 dash into u2, right? n1 and n2 are functions of x, that is why u dash is this. So I can write it as, again, in the matrix form as n1 dash n2 dash into u1 u2. Alright, and this we write as another matrix B transpose into D. Now this matrix B is called, where B is called strain displacement matrix, where B, which is equal to n1 dash n2 dash, it's a column matrix again, so it's a vector actually for two noded bar element, so is called strain displacement matrix. Strain displacement matrix. So this is another important matrix that comes frequently in any finite element, finding any formulating any finite element B matrix, which is called strain displacement matrix. Why we are calling it strain displacement? Because u dash is my strain, you all know, du dx, and that is related by this matrix to the nodal displacements, which are basic unknowns. That's why we call it, this matrix relates the strain to the nodal displacements. That's why we call it as strain displacement matrix. Clear? Now our job will be to write down the weak form for the element. So let's go to the next page for that purpose. So let me write the element equation using the Galakin's method. So element equation using Galerkin's method. So in Galerkin's method, what we will do? We will write down the residual, of course. And we know what is the residual. We know that residual at any point, which is we denoted by E, So Ex is my, I know that ddx of AE into du dx plus Q. This is my weak form, and this is the value of error, right? Because we are using approximate solution, I mean residual. Okay, so again I will equate the weighted residual to 0 over the element, just like the classical method. And therefore, now while writing the weighted residual, we should just remember that our shape functions act as the weight functions. This we have already seen here. So in FE formulation, the shape functions perform the role of weight functions. Okay, so weight functions are directly the shape functions. Therefore, we will write the weighted residual as what? We will write, so the weighted residual, so weighted residual will be so the weighted residual will be integration of this, right? Integration of the residual multiplied by the weight function over the domain. So my integration will be from x1 to x2, and my weighted residual will be ddx of AE. We'll write du dx as u dest, okay, into ni plus q into ni, because shape functions are my weight functions, dx, and this will be my 0, right? Weighted residual will be 0. Now this first term I will use integration by parts formula, and therefore I will get, so first term I will get the boundary terms I will write first. So what I will have AE into ni at x2 into u dest x2 minus AE ni x1 into u dest x1, these are my boundary terms, minus integration of x1 to x2 AE u dest and ni dest, right? Ni dest x dx. You remember the integration by parts formula we have discussed earlier, so my order of differentiation will change now, and then I have q integration of x1 to x2 q dx, which is 0. Now I know that this term AE du dx at x equal to x2 into n I x2 this term AE into U dash at x2 is my natural boundary condition, right? You remember that AE du dx at x equal to x2 is P2 and AE du dx at x equal to x1 is minus P1. So let us put those values now. So therefore this gives me P2 minus P1. So this is minus P1, okay. Minus P1, right, minus this thing x1 x2. Okay, I have this into ni, I'm sorry, ni x2. Let me rewrite it. So I have P2 into ni x2 minus this AE U dash x1 was minus P1, so this will be P plus P1 into ni x1, right, minus AE U dash ni dash x, of course, dx plus integration of q dx is 0, right? So now I will write this equation for both n1 and n2. So for I equal to 1, I will have what? P2 into n1 at x2 plus P1 into n1 at x1 okay, minus this quantity x1 to x2 AE U dash n1 dash x dx plus integration of q dx is 0. This is one equation, say equation Roman 1, and I equal to, for I equal to 2, I have P2 into n2 x2 plus P1 into n2 x1 minus x1 to x2 AE U dash n2 dash x dx plus I have done a mistake. This should be ni, right? This should be ni. There should be an ni. Let me write this. let me write this ni, okay, nix actually. So I should write here also nix dx, nix dx equal to 0, and here also n1x dx equal to 0. And here I have q into n2x dx equal to 0. This is my equation 2. So now let us see that we have noted that the shape function n1 at x2 is 0. You remember that we had drawn the shape of the shape functions. We have seen that n1 is 1 at x1 and 0 at x2. Similarly, n2 is 0 at x1 and 1 at x2. So we will put those values now in this equation, in these equations. So therefore I can get p2 into 0, so that term will not be there. Then p1 into n1 at x1 is 1, so p1 minus this integration x1 to x2 AE. Okay, let me also do one thing. Let me take this term, this integral term, to the right hand side and these two to the left hand side, the force terms, and then just write in the other way around. That means I will write this in the left hand side and this in the right hand side. Okay, in that case what I'll get this AE, integration of AE into u dash n1 x dx from x1 to x2 is my will be my what? This term will be 0, only this term will remain. So p1 into 1 plus q n1 x dx. So I will have this equal to p1 plus integration of x1 x2 q n1 x dx. Is not it? And similarly for the shape function n2, what I'll get this term will become p2 into 1, and this term will be 0 now because n2 at x1 is 0, and this term will be there. So okay, I have missed the limits here, I'm sorry. So I will write AE u dash into n2x dx will be equal to p2 plus integration of x1 to x2 q n2x dx. Alright, so say this is my equation 3, and equation 4. Now we remember that what is my u dest in terms of shape function? What was my value of u dest in terms of shape function? We know that u dest is B transpose into D, right? B transpose into D, and so this value u dest equal to this n1 dest n2 dest into D, that we will write in these equations 3 and 4. In that case, what I'll get? I'll get, therefore, I'll get integration of x1 to x2. U dest I will write in terms of n1 dest and n2 dest, okay? And I will also combine these two equations in matrix form. Alright. Then what I can write? I can write that integration of this n1, okay, let me put this value here, AE into u dest is my what? U dest is B transpose into nodal displacement vector. So B transpose was my n1 dest, n2 dest into u1, u2 into, from the first equation I will get n1x, and from the second equation I will get n2x. So if I combine them, then I will get, in matrix form, I will get n1x and n2x, right? Into dx will be equal to what? Will be equal to this p1 and p2 when we will arrange in matrix form. I will get p1 plus and p2, and then I will get a matrix comprising of this term and this term, right? So matrix comprising of this term and this term, which I can write as integration of n1 and 2 into q dx from x1 to x2. Is not right? Now from here what I get, I can now write this as, what is this? This is B transpose, okay? And this is my D matrix. Therefore I can write this as, by keeping the matrix so that the matrix multiplications are possible, I'll write n1 dest, n2 dest, okay, n1 dest, n2 dest, I think I have missed one point, that this is differentiation of n, okay, which I missed here. Again, silly mistake, you need practice, that's why. So u dest, n1 dest, u dest, n2 dest. So these are my dashed thing. Okay, so n1 dashed n2 dashed into AE into, I will write n1 dashed n2 dashed into the d vector u1 u2, okay, is equal to what? This is my nodal load vector p1 and p2, is not it? And these terms are also will give me force, right? Because it is q into it is a surface traction integration over the length, so it will give me again the load vector for the surface traction at the nodes. So I will call it, say, fq1 and fq at node 2. Okay, so these are basically force vectors. Okay, this dx should be there. Now you see, this u1 and u2 are basic unknowns, nodal unknowns, and they are taken as unknowns, so they are not functions of x because they are at nodes. So the integration has to be done for this part only. Therefore, what I will write, I will put this dx here. Okay, so therefore I can write this as x1 x2 into n1 dashed n2 dashed into AE into n1 dashed n2 dashed dx, this whole thing into our u1 u2 are my nodal load vectors, equal to, say, finally f1 and f2, where this f1 includes both the concentrated load and the contribution of the surface load. Okay, so now in order to make the matrix multiplication possible, I will write this matrix here, this column matrix in the beginning and row matrix towards the end. Otherwise this will be a scalar, right? And we know that the stiffness of an element is a matrix, not a scalar. So what is this matrix? This is my B matrix, and this is AE, the axial rigidity, and this is my transpose of B matrix. So when I compare this equation with K times nodal displacement equal to nodal load vector, so I can get that the element stiffness is given by this B matrix into AE. AE is my axial rigidity. So what I can do is I can keep E here and A I can take to this side, so that I get a matrix called Constitutive Matrix into B transpose into dV, because you know that my A times dx is my dV, infinitesimal volume. Okay, now this, in general, we write this as a constitutive matrix, which for the bar element we have got only E. It's a scalar for a bar element, but in general for 2D or 3D elements it will be a matrix containing the material properties of the element. Just like here, E is the modulus of elasticity of the bar material. Similarly, in a 2D problem, I will have a matrix, okay, instead of a scalar. So that's why this is my general formula of the element stiffness matrix, which is given by volume integral of my B matrix times the constitutive matrix times the transpose of strain displacement matrix. Okay. So now let us find out the value of this element stiffness matrix for our bar by using this B matrix in this equation. Okay. So we remember that B matrix is, we have B matrix is N1 dest N2 dest, right? Now you remember my N1 was what? X2 minus X by L, okay? And N2 was X minus X1 by L. So therefore, what is my N dest? That means N1 dest equal to d of N1 dx. So this will give me minus 1 upon L, right? Minus 1 upon L. Similarly, N2 dest will be 1 upon L. So now let us put these values in the element stiffness matrix equation. Therefore, what I'll get K matrix of the element as integration of over the length integration of this matrix. So I have minus 1 upon L and 1 upon L into AE into minus 1 by L 1 by L, right, dx. So integration of dx is x, and over the length L it will be just L, right? So therefore, if I now do the matrix multiplication, what I will get? I will get let us do the matrix multiplication. X1 to X2, this into this, so I will have 1 by L square 1 by L square minus minus plus, then this will be minus 1 by L square, then this will be 1 by L into minus 1 by L, so minus 1 by L square, and this will be 1 upon L square 1 upon L square into AE dx, right? So this I will get when I integrate dx over L, I will get 1 L here, so that L and this L square will cancel, So I will get ultimately AE into L into this matrix, 1 upon L square minus 1 upon L square minus 1 upon L square and 1 upon L square. So by cancelling this L, I can take this L square out, so I will just get A by L into 1 minus 1 minus 1 1. So this is the same stiffness matrix you had earlier derived by using principle of mechanics, is not it? But this gives me a general method which I can use in any kind of element. Okay, that's why this is a very important formula. This general expression for element stiffness matrix is a very important formula. It is given by integration of volume integral of B into C into B transpose dV, where B is my strain displacement matrix and C is my constitutive matrix. Okay, constitutive matrix. Now let us find the consistent nodal load vector for this part. This is already a nodal force, P1 and P2. Now the surface traction I need to convert into nodal load vector FQ1 and FQ2, and I know that this is given by this integral N1 Q dx. So our next job is to find the consistent nodal load vector. Consistent nodal load vector. For surface traction, for traction. Now for that we'll find out this integral. Okay, so I have my FQ vector as integration of x1 to x2, my B matrix N1, not B matrix, it is my shape function matrix N1 N2 into Q dx. Right, now let us put the value of N1 and N2. So by putting the value of N1 and N2, I get N1 into Q, N2 into Q. These are my terms, right? So N1 was x2 minus x by L, and N2 was x minus x2 by L, Q dx. Okay, now if Q is a constant, suppose I have a uniformly distributed load, then this Q I can take outside the integral sign. Okay, for constant Q, that is Q is not a function of x, I can write FQ vector as Q into this matrix, integration of x2 minus x by L dx over the length, and this integration x minus x2 by L over the length. Is not it? Now let us find out these integrals separately. So x2 minus x by L is integration of x2 minus x by L is what? x2 by L dx minus x by L dx. Let me put dx outside over L. So this will give me what? Let me put x2, sorry, x1 and x2. Let me put the limits, x1 and x2. So this is x2 by L into x2 minus x1, right? Integration of dx is x, by putting the limit this I get, minus x square, x dx is x square dx, so 1 upon L x square dx, so x2 square minus x1 square by 2, right? So this will give me, let me take 1 upon L common, then I get x2 square minus x1 x2 then minus x2 square by 2 minus x1 square by 2. So let me factorize this, a square minus b square, so x2 plus x1 into x2 minus x1 by 2, so half of this. So this will give me the first value, and after I now I can take x2 common here also, so 1 upon L, here I get x2 into x2 minus x1 minus x2 minus x1 into x2 plus x1 by 2, right? And this will give me, if I take x2 minus x1 common from both the terms, 1 upon L x2 minus x1 common, then I'll get x2 minus x2 plus x1 by 2. Okay, and this gives me 1 upon L into x2 minus x1 into, this is twice x2 minus x2 minus x1, so twice x2 minus x2 minus x1 by 2, and this gives me what? This gives me 1 upon L into x2 minus x1 is L into, what is this? Twice x2 minus x2 is x2, so x2 minus x1 by 2, so this is L by 2 again. Okay, so finally this integral gives me ultimately L by 2, and hence I will have my FQ vector of first term, so FQ, which is equal to FQ1, FQ2 is given by, you see, Q times this integral, and this integral is L by 2, so the first term will be QL by 2. Okay, also in a similar manner, you please find it yourself, we can write that this integral x minus x2 by L dx, integration of x minus x2 by L dx from x1 to x2 is again, you will get QL by 2, and hence my FQ vector will be just half of the total load at one node and half of the total load at another node, provided Q is constant. Okay, so if I have a bar which is acted upon by a constant surface traction, uniform surface traction, then there is the value. If it is a linear, then of course Q will be a function of x, and I will have to do the integration by writing Q in terms of x. Okay, so this is how we can find out consistent nodal load vector. Okay, so this is another thing we have got. So this is called my consistent nodal load vector, and for a constant uniformly distributed axial load, I get their values as QL by 2 and QL by 2 at the two nodes. Alright, so this is how we can formulate the bar element using the Galakin's method. Okay, and we have seen that by two noded element I can find out the value of the element stiffness matrix for this two noded element. Now one question arises, if I have a long bar, I know that in an axial deformation problem, we know that from our analytical solution that my actual deformation varies cubically over x, but here we are taking the element variation of displacement over the element as linear. Okay, so if I use a single bar element for a bar, then there will be some errors. Okay, my results will not be very correct. But if I take many small elements to discretize a bar, suppose I have a bar, say I have a bar of some length of constant cross section. So if I take only a single element, only a single bar element, okay, with only two nodes at the two ends, then my solution will not be good. But if I discretize it with finer mesh, that means instead of a single bar, suppose I take many bars, many bar elements, okay, and then we find out the element stiffness matrices of every bar element, and then we find out the global stiffness matrix, okay, by assembling the element stiffness matrices. Then our result will be more accurate. Another way is to have a higher order finite element. Suppose instead of a linear finite element, what we had assumed here, that in this case so my other alternative is to define a higher order element. Say for our case, what we had assumed, u was within the element was a linear function, a0 plus a1x, right? And then by using weighted residual method, we have derived the finite element equation. I can have a three-noded bar element with a quadratic function, say a0 plus a1x plus a2x square. In that case, I may define a three-noded bar element also. Okay, say I have a bar element having three nodes, two at the ends and maybe one at the middle. In that case, I will need to define three shape functions, and by using them, by following the same process, we can find out a higher order element, okay, quadratic element. And if I use quadratic element, I need not have a very fine mesh to get a better result. I can have a coarse mesh. Say here how many elements I have taken, 1 2 3 4 5 6 7 8 9 elements. Maybe in that case 5 elements will do good job. Okay, so to increase the finite element accuracy, solution accuracy of finite element model, we can either go for more finer mesh with a simple element, or I can have higher order element and a coarser mesh. Usually we prefer simple element because they converge much more easily, and also the computational cost becomes, for small model, if I use a lower order element, computational cost will be less. But if it is a very complicated model, then sometimes using higher order element and a coarser mesh may give me a less computational time, so less computational cost. Okay, so in actual practice, what kind of FEM model you will use, that depends on many factors. And this being an introductory course, since we are not actually doing finite element modeling using some programs or some free or commercial software, those issues we will not be able to discuss in this course. But basically you have learned that we can generalize the element stiffness matrix formulation by using Galerkin's method. The same thing we can do by using Rayleigh-Ridge method also. In our next class we'll see that. And we have also learned that either to increase the finite element accuracy, solution accuracy, I can either use more number of simple elements or I can use less number of higher order elements. So with this we come to the end of this lecture. I hope you enjoyed it and you understood the basic concepts. So you need to practice these derivations to remember or understand more fully. I hope you will do that. Thank you very much.